Hi, I'm Andy Meyer. I'm recording this demo as a proof of concept for the Project 5 for real-time and embedded systems. I've decided to do something a little bit different for my project for no particular good reason other than that I wanted to. And what I have done is taken the demo board and I've connected it to a VGA monitor, and I'll cut the video in a moment over to what the monitor displays in a moment, so that we can see that in a little bit more detail. But for just a moment, I'd like to go over the signals, and then we'll go over the code, and then finally show the final product. So pictured here, we have the demonstration board from the class, and we have a small video adapter that is just a series of R to R digital to analog converters. And probed here are a couple of different pins for my logic analyzer, whose outputs you can see in the background. So if I take a quick capture, then we get this plot, and shown here is in white the horizontal synchronization signal, in brown the vertical synchronization, and then in red is the most significant bit of the red color channel, and in yellow here, counterintuitively, is the most significant bit of the blue color channel. So if we zoom this out, we can see there's a lot of H-sync pulses between any given pulse of another color. And there's no V-sync shown here because there are so many H-syncs between each V-sync. If we zoom out on this capture, we can see that there are quite a few horizontal sync pulses between every vertical sync pulse. And the reason for this is that the horizontal synchronization pulse goes out once for every scan line on the monitor, or about 480 times for the visible part of the screen, and a total of 525 times including the vertical blanking period. And then the V-sync signal only goes out once every frame, and we can see that in between the V-syncs there's this blanking where no drawing goes on around a short area for every single V-sync pulse, and these are the blanking periods. If we zoom in further to see just one horizontal line, we can see that the same occurs around the horizontal synchronization pulse, where the polarity of the V-sync pulse doesn't matter here, but the color lines drop to 0 in order to fulfill the VGA timing specs. And if we measure some of these using the logic analyzer software, we can see that we're 100% within the specification. The specification lists a horizontal front porch, which I've highlighted in red, and we'll bring up the measurements here, which is 2.021 microseconds, and it needs to be 0.63. If we take another measurement, we can see that the length of the horizontal sync pulse is 3.181 or 3.812 microseconds, which is within spec. And the horizontal front porch between the rising edge of the sync pulse and the rising edge of the first pixel is 1.886 microseconds, which is also within spec. So we generate these signals with two different timers that I'll show in the code in a moment, but we can see that this generates a valid looking signal with correct timings. Shown here in this somewhat boring, very large comment block is the configuration for the timers used to generate the signals we saw in the previous section. So timers 2 and 4 are used, which are just the basic general purpose timers on the STM32L4. And timer 2 produces the horizontal sync, timer 4 produces the vertical sync. Timer 4 is actually set in slave mode to timer 2 such that the timings of the vertical sync pulse will always be exactly in sync with the timings of the horizontal sync pulse. And this prevents the video frame from sliding or appearing corrupted on the monitor. The sync pulses are produced using capture compare channels, and no interrupt is required to produce the output value. So in order to keep the monitor on and keep a video in frame, no CPU time is required whatsoever. There's quite a bit going on in here, but it's relatively well documented. We set up and make sure that we're actually in the frame so that we don't violate drawing any colors in the blanking periods. And then we go into a carefully timed loop with a couple of knobs to basically move data from memory onto the appropriate I/O ports. And then we turn off the color pins once we're done drawing. And then at the end of this, we go through and actually update some extra information that has to do with rendering to the screen for a different interrupt routine. If we go back and look past the timer configuration and we have a look at the rendering code, we can see that all we do here is select sprites that need to be drawn. Function has only about 7 microseconds to run for each 640 by 480 line, and we run it about 3 times for every line that we physically draw. So really we have on the order of 21 microseconds to produce a line, which is not very long. Even at 80 megahertz, that's only maybe 1,000 clock cycles. We draw the sprite by copying things 4 bytes at a time. This makes use of the ARM processor's 32-bit data bus, and this makes the copying much more efficient because we can only fit so many instructions in at once. So this keeps the bus saturated as we go. This is where if we were writing a game or making something animated, this is where we would compute the data for the next frame. And that's exactly what we do. So in this function, we first clear up some interrupt masks to make sure we don't get called a second time. And then we basically take 2 particle entities and update them based on their position and velocity. And then we basically just make sure that each moving particle bounces around the screen and doesn't go off it. Okay, and last but not least, let's show off what it actually does. So we can see here that the only connections going into this adapter, which is simply an R2R DAC ladder and a small amplifier to prevent the signals from degrading over the VGA cable, we can see we have our color data going in, power, and 2 synchronization signals, the H and V sync, and that is all. We're only using 2 bits for the color. We have 1 color in red, 1 color in blue, so we can make red, blue, purple, and black. So following this cable down to the monitor, we can see it's the only thing plugged in, and this is what is displayed. There are 2 sprites with a test pixel pattern that are bouncing around the screen like an old DVD player, but a lot faster and less cool, but way more satisfying. And on the side of the screen here, we can see that there's some blurriness or horizontal shaking, and that is because this monitor is defective. I didn't know this when I started working on it because I don't have anything else that outputs VGA. Turns out it's a really old spec, and I've gotten rid of all my hardware that's that old except this recycled monitor. The only way that I can tell that it's broken is because we're in spec on the timing, with a jitter of about 0.01 microseconds. That's all there is to show for this demonstration. I hope you've enjoyed and that this will count for some points. Thank you very much for watching.